Hello guys, happy new year to you all. We wish you the best of it. Prosperous year ahead. So you are welcome to Paul Mathematics Academy. In today's video, I'll be explaining or I will be teaching the group theory. So that's abstract algebra 1. So I'll be teaching the group theory. Alright. And then I'll be teaching the introductory part now. Alright, now let's get started. For us to understand the group theory, we must know what we call an algebraic structure. So, what is an algebraic structure? Alright, an algebraic structure. So, let me quickly explain that. You can say, let X be a non-empty set. Be a non-empty set with binary operation asterisk. That is X, an asterisk is an algebraic structure if some properties are hold, or you can say it under some axioms. Alright, so I said let X be a non-empty set with a binary operation asterisk, that is X, asterisk is an algebraic structure if some properties are holds, or we can say it's an algebraic structure under some what? Under some axioms or properties. Alright, since we already know the definition of a group of an algebraic structure, now algebraic structure is of two types: the algebraic structure with one binary operation and the algebraic structure with more than one binary operation. So, example of algebraic structure with one binary operation. Algebraic structures algebraic structure with one binary operation. So it includes the groupoid, a semi-group, monoid, and then a group, a full group. Alright, so these are algebraic structure with one binary operation. And then we have algebraic structure with more than one binary operation. So under that, algebraic structure with more than one binary operation, we have ring, we have field, we have vector space, and so on and so forth like that. But our scope is not beyond the group. Are you getting me now? Because we are dealing with the group theory. So we are dealing with the abstract algebraic one. So we are dealing with the group theory. So I'll be explaining the algebraic structure with one binary operation. With one binary operation. Now let me explain a group. 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 So what is a group? All right, so let's start with the definition. Like I said, let G be a non-empty set under the operation asterisk. This operation asterisk means it can be any operation given to you. You can be given a multiplication, you can be given an addition, you can be given subtract, any operation given to you to check whether the algebraic structure is a group or not. Are you getting me now? So under the operation asterisk, or you say under the binary operation asterisk. All right, then the couple G, an asterisk is said to be a group if the following axioms are satisfied. All right, for it to be a group, some properties or some axioms have to be satisfied. Are you getting me now? So I say let G be a non-empty set under the operation asterisk. So the couple G, asterisk is said to be a group if the following axioms are satisfied. And now I'll be listing the axioms we are talking about. The first axiom is the closure property. That is, you gonna take two elements from the group given to you or from the algebraic structure given to you. So A, then you combine the two elements together. So for all A, comma B is a member of G, implies that A asterisk B is a member of G. So if we combine the two elements together, A and B, if the result is a member of the G, of the group G, then we said it is closed. Are you following me? But if it's not a member of G, then we said it's not what? It is not closed. Are you following me? Sorry. So if after combining A and B, and then the result is not a member of G, then we said the algebraic structure is not closed under the operation given to you. Are you following me? Then the next property is the associative property. Associative property, that is, for all A, B, C a member of G, implies that A asterisk B asterisk C is equal to A asterisk B asterisk C. So if they are equal, then we said it is what? It is associative. We said it is associative. The third property is the identity property. That is the existence of the identity element. So we use E to represent that. So the existence of the identity element E. That is, if the group or the algebraic structure given to you has an identity element. Are you getting me now? So it's one of the property of a group. For it to be a group, it must have an identity element. So we can now say implies that E asterisk A will give you A. That is, whenever your identity element combine with any element in that your algebraic structure, is going to give you that element itself. Are you following me? That's why I say E asterisk A is giving me A. That shows that E is the identity element. Now, for instance, the set of natural numbers, you get set of natural numbers. So under the operation multiplication, let me just say under the operation multiplication. So if I use 1 to multiply all the number in set of natural number, yeah, it's going to what? It's going to result to that same number. That shows that 1 is the identity element of a natural number. Are you following me? So I'm still going to explain that. So let's finish the definition for a group. All right, the last property for it to be a group is what we call the inverse property. Inverse property. That is, each element or all elements in the algebraic structure must possesses their what? Their inverse in that what? In that structure given to you, or in that group given to you. Are you following me? Each element must what? Must possesses their inverse in the given set. So if their inverse is not in the given set, it shows that it's not a group. So for it to be a group, their inverse must present in the what? In the given set. So it implies that, so I'm using A inverse asterisk E is going to give me what? A inverse asterisk A is going to give me E. That is, whenever I multiplied A inverse by A, it must give me the what? It must give me the identity element. Are you following me? So it must give us the identity element. So take note of that. So those are the 4 properties of a group. So for a set to be a group, or for an algebraic structure to be a group, it must possesses these 4 properties. That is, these 4 properties must be what? Satisfied. Now we have a special case. In a special case, when the commutative property is satisfied, special case. When the commutative property is satisfied, then we said it's an what? Abelian group. Is an abelian group, or you call it commutative group. Are you following me? So if the commutative property is being satisfied, then we said the algebraic structure is an abelian group, or you call it commutative group. Don't forget the commutative operation. A asterisk B must be equal to B asterisk A. No matter how you arrange them, they must be equal. So if the commutative property is being satisfied, then we said it is an abelian group. So before I move to the next part, let's quickly check again. I said an algebraic structure. So let X be a non-empty set with a binary operation asterisk, that is, X, an asterisk is an algebraic structure if some properties are holds, or is an algebraic structure under some what? Some axioms. And then I said algebraic structure with it can be of 2 binary operations, it can be of 1 binary operation. So I gave example of algebraic structure with 1 binary operation, which is your groupoid, your semi-group, your monoid, and a group itself. And I gave example of algebraic structure with more than 1 binary operation. I say ring, field, vector space. Are you following me now? So then I said we are dealing with a group theory. That is, I will be dealing with the algebraic structure with only 1 binary operation. Then I explained group. I said let G be a non-empty set under the operation asterisk. The couple G, asterisk is said to be a group if the following axioms are satisfied. We have the closure axiom, or the closure property, the associative property, the identity element, the existence of the identity element, and the existence of the inverse element. So if those 4 properties are satisfied, then we say the algebraic structure is a group. Now, in a special case, when the commutative property is satisfied, that is A asterisk B is equal to B asterisk A, then we said the algebraic structure is an abelian group or a commutative group. So now let's move on to the next part. So let's quickly explain groupoid, a semi-group, and a monoid. Now, what is a groupoid? Now, for an algebraic structure to be a groupoid, the first property only it's said to be satisfied. So, for it to be a groupoid, I can say when just only one property among those four properties is being satisfied, then we said it is a groupoid. Are you following me? Then we said it is a groupoid. Another one is our semi-group. Semi-group. When two axioms are satisfied, we then said it's a semi-group, but not a full group. Are you following me? Is a what? Is a semi-group. Let me just say when the first conditions or when the first axioms are satisfied, let's say the closure property and the associative properties, when they are satisfied only and other properties are not satisfied, so we call it a semi-group. Are you following me? So it's not a group, but it's a semi-group. And then for groupoid, what will be satisfied? Maybe the only first property will be satisfied. So when the only first property is satisfied, that is the closure property, is the only one satisfied, then it's not a what? It's not a group, but we call it a what? A groupoid. That is only one property is being satisfied. Are you following me now? So another one is what's it called? Your monoid. So what is now your monoid? Monoid, when the three properties or when three axioms are being satisfied, then we said is a what? Is a monoid. When the first three axioms are satisfied, we said is a monoid. Are you following me? So for it to be a monoid, the three properties must be satisfied. It must be closed, the associative property must be satisfied, and it must have an identity element in the group. Are you following me now? And then for it to be a full group, the four properties must be satisfied. Now take note, an invertible monoid is called a what? It's called a group. If I say an invertible monoid, it's called a what? It's called a group because there is an existence of the what? Of the inverse element in it. Alright, so that's just that about your groupoid, your semi-group, and your monoid. Once again, your groupoid satisfies, for it to be a groupoid, your algebraic structure will satisfy just only one property or axioms. And then for it to be a semi-group, your algebraic structure will satisfy the two what? Will satisfy two axioms. And for it to be a monoid, your algebraic structure is going to satisfy the three properties: the closure, associative, and then the existence of your neutral element or your identity element. And then for it to be a full group, the four properties must be satisfied. Or we can also say it, an invertible monoid is also a what? Is also a group. So, and then in a shortcut way, I can say a groupoid has only one satisfies only one condition, which is the closure property. So I can now say a groupoid with the associative property is a what? Is a semi-group. That is, we are adding another what? Another property to it. And I can also say that a semi-group with an identity element or your neutral element is called what? It's called a monoid. And I can also say a monoid with inverse elements is also what? It's also a group. So put that in mind. All right. So now let's look into some examples. Investigate. But before I write investigate, let me write this. Illustration 1. So let G be a group. And is equal to set of integers under the operation plus. Are you getting me now? So let G be a group which is equal to set of integers under the operation plus. So your question is that investigate whether this is a group or otherwise is an abelian group. So I want to investigate if it is a group or otherwise it is an abelian group. So if you want to start this solution, so I will be writing down some set of integers we have. Your set of integers starts from negative number. So let me just write dots. So I write -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, dot. Are you following me now? So now let's check all those axioms for us to show whether it is a group or otherwise is an abelian group. All right, so let's start with the closure property. For you to check whether it's a group, you must undergo all those processes, all those axioms. So the closure property, let's check whether it holds or not. So the closure property, which implies that for all AB, a member of your, now I'm using natural set of integers, now implies that A asterisk B is a member of your set of integers. All right, now this asterisk, the operation here is now plus, not asterisk again. So I'm going to use plus, then I'm going to take two elements from this set of integers. Are you following me now? So I'm going to have A plus B. Will it be a member of Z? So now let's take two elements from this. I'm going to take -5 and I'm going to take 3. So taking -5 and 3, let's check whether our results will be among the set of integers. So I'm taking -5 plus 3. So will it be a member of this? -5 plus 3 will give us -2, who is a member of set of integers. Then the closure property is being satisfied. So we move to the next property, which is the what? The associative property. So moving to the associative property now implies that for all a comma b comma c, now I'm using set of integers now, it is a member of the set of integers. Are you following me now? So now implies that a asterisk b asterisk c is equal to what? Is equal to a asterisk b asterisk c. Now don't forget the binary operation here is now what? Is now plus, not what? Not asterisk again. So I'm going to change that to plus. A plus b plus c will it be equal to a plus b plus c. So what can I take now? Okay, let's say my a is minus 5, my b is 3, and my c is 1. So if my a is minus 5, my b is 3, and my c is 1. So I'm going to have minus 5 here, plus 3, plus 1. So this implies minus 5 plus 4, which is equal to minus what? This is minus 5 plus 3. So that will be minus 2 plus 1. Alright, so minus 5 plus 4 will give us minus 1, and the minus 2 plus 1 will give us minus 1. We can see that the associative property also holds. Alright, what is the next property we have to check? We have to check the what? The identity element. Now, what's our identity element here? Our identity element is 0. Why? Because if you add 0 to all members of this set of natural numbers, it's going to remain the same. Minus 5 plus 0 is minus 5. Minus 4 plus 0 is minus 4. Minus 3 plus 0 is minus 3. Minus 2 plus 0 is minus 2. Minus 1 plus 0 is minus 1. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. 0 plus 4 is 4. 0 plus 5 is 5. So it is the neutral element. If you add 0 to all numbers here, the number is not going to change. So we said the identity element is 0. So there is an existence of the neutral element or the identity element. Alright, what next? Let's check for the inverse. Let's check whether all the elements here have their inverses or possess their inverses here. Alright, don't forget your inverse property. I said A asterisk A inverse will be equal to what? It will be equal to E. That is, if you combine your A and your A inverse together, it must give you your identity element. Take note of that. So what will be the inverse of minus 5? Inverse of minus 5 is what? That is minus 5. What will combine with minus 5 to give you 0? So that will be 5, because minus 5 plus 5 will be 0. Are you following me? The inverse of minus 4. Minus 4 plus 4 will give us 0. Inverse of minus 3. Minus 3 plus 3 will give us 0. Inverse of minus 2. Minus 2 plus 2 will give us 0. Inverse of minus 1. Minus 1 plus 1 will give us 0. Are you following me now? So let me just quickly do something now, So A asterisk B is equal to what? Is equal to A plus B according to the operation we are using, plus. Then turn B to A inverse. So that will be A asterisk A inverse is equal to A plus A inverse. And your A asterisk A inverse is your identity element E. So E is equal to A plus A inverse. Then if you make A inverse the subject of the formula, so you have A inverse is equal to E minus A. Alright, and your E, which is the identity element, is 0. So A inverse is equal to what? 0 minus A. That is minus A. So if you take any element, let's say you want to find the inverse of minus 5. So minus 5 inverse will be what? Minus 5. So that will be minus into bracket minus 5. That is A is minus 5. So minus 5 inverse will now be equal to what? Positive 5. Then inverse of minus 4, that is, if you want to find the inverse of minus 4 inverse will be what? Minus into brackets minus 4, which will result to 4. Let's say I want to find the inverse of 3. So inverse of 3 will be what? Minus 3, because minus 3 plus 3 will give me 0. So the existence of what? Of inverse element for each element in the set of integers. That is, all elements are invertible. So it is absolutely a group since all these 4 properties are being satisfied. But what we are about to do now is check whether it's an abelian group or not. So how are you going to check whether it's an abelian group or not? So using the property of the commutative or the commutative property, I've explained that before, which is A asterisk B, will it be equal to B asterisk A? Alright, so don't forget our asterisk is plus. So A plus B, will it be equal to B plus A? That's what we are about to check. Alright, so let's take two elements. I said A is -5 and B is 3. That's what we'll be using this morning. So -5 plus 3, will it be equal to 3 plus -5? Yes, this is absolutely equal. -5 plus 3 will give us -2. And then 3 minus 5 is also give us -2. So the commutative property holds. So since all these properties are satisfied, then we said it is an abelian group. So set of integers under the operation addition is a what? Is an abelian group. Have that in mind. Set of integers with a binary operation plus or addition is an abelian group. Alright, now let's check for set of natural numbers under the operation multiplication. Let's check whether it is an abelian group or not. Or it is a group. Let's check whether it's a group or rather an abelian group. Alright, so I want to take set of natural numbers under the operation multiplication. So I want to check whether it is a group or otherwise it is an abelian group. So now let's run those properties again. As usual, the closure property, let's check whether it's satisfied or not. So before that, let me write some natural numbers down. You know, your natural number starts from what? 1. It does not start from 0. So 1, 2, 3, 4, 5, 6, comma, dot, 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 to infinity. Alright, let's check whether the closure property holds here. So that is, given A asterisk B, will it be a member of G? So of G, which is natural number we are talking about. Alright, so A asterisk B is now A multiplied by B. A multiplied by B, will it be a member of natural number? Or will it be a member of the group? So A times B, so let's take 1 and 3. So 1 and 3, if I say 1 times 3, you can see it's equal to 3, which is a member of natural number. But you know, if you use 1 to multiply everything here, you are still going to get the same thing. So let me use another number. Let me use 2 and 4. So 2 times 4 will give me what? Will give me 8. Will give me 8, which is a member of natural number. So the closure property holds. Now let's check for the associative property. Now the associative property A asterisk B asterisk C, will it be equal to A asterisk B asterisk C? So let's take A to be 2, B to be 3, and C to be 4. 2 asterisk 3 asterisk 4. Will it be equal to which is 2 asterisk 3 asterisk 4? Don't forget your asterisk is multiplication. That will be 2 times, now 3 times 4 is 12. 2 times 3 is 6 times 4. So 2 times 12 is 24. 6 times 4 is 24. So the associative property holds. Now let's check for the identity element. So the identity element here is 1. So identity element, or you call it neutral element, is equal to 1. Because if you multiply 1 with all numbers here, the number will not change. So what do we call a neutral element itself? A neutral element is the element that you combine with all other elements in the set given to you that will not change the element. Are you getting me now? So if you combine the natural number, the natural element with any element in the group, is not going to change that element. So 1 times 1 is 1, 1 times 2 is 2, 1 times 3 is 3, 1 times 4 is 4, 1 times 5 is 5, 1 times 6 is 6, 1 times 100 is 100. It's not changing that element. So the identity element is 1. Now let's check whether all the elements here have their inverses. Alright, what was the inverse of 1? The inverse of 1 is 1. Okay. What's the inverse of 2? That's where the question is. What are you going to multiply with 2 to give you 1? And that's 1 over 2. So we can see that 1 over 2 is not a member of natural number. And that is what? That is a rational number. Are you following me now? So it's not a member of natural number. Then it's not a group. So let me just write down the identity stuff. I mean the inverse. So A asterisk A inverse is equal to E. Don't forget. So A asterisk B is equal to A times B. The operation we are using is multiplication. So replace B by A inverse. So that will be A asterisk A inverse is equal to A times A inverse. And A times A inverse is E. So you have E, which is equal to, so A times A inverse, A times A inverse, and our E is 1, so I have 1 is equal to A times A inverse, then divide both sides by A, so you have A inverse is equal to 1 over A. So now if I find inverse of 1 is 1 over 1, which is 1. Now inverse of 2 will be what? 1 over 2, which is not a member of natural number. So inverse of 3 is what? 1 over 3. And 1 over 3 is not a member of natural number. So it's not a group. Hence, it's not a group. Since all the element does not possess their inverses in the given set, so it's not a group. Are you getting me now? But it's a what? You can see it's a monoid because it satisfies the 3 properties. It's a monoid. It's a monoid. It's a monoid. So, all right. So that's that about that. So when you can check for rational numbers, you can check for complex numbers also on your own. So when you're studying it, so that will serve as your exercise. So when you're studying that, so you can check for set of integer. Set of complex number, set of rational numbers, set of irrational numbers. So you check whether they are group or not, or otherwise whether they are an abelian group. All right. So that will be the end of our lecture. So that's under the introduction to the group theory. So we shall continue in our next class. So if you like this kind of video, please don't forget to subscribe to my channel, like my video, comment, share my videos to your friends. So please subscribe. That's the only way we can use it. Subscribe. Thank you. God bless you. Bye. Happy New Year.